Off we go. So this week, again, more with distributions. In particular, we'll focus on the normal distribution and a related idea called the central limit theorem. Please be sure to read the textbook, and there's a bunch of chapter 6 videos and chapter 7 videos, some by me and some by others. And then I usually have more videos than what I post here in my YouTube playlist, which is available in the course information section. Good morning, Deanna. So let's go to the notebook. All right. So before we get into the normal distribution and sampling distributions, I just want to give you a reminder about what the heck a distribution is. And when we talk about the idea of a distribution, really what we're referring to is a few different things. It's kind of the shape of a histogram. Where we're trying to understand how the data is spread out and bunched together. And there's just infinitely many shapes a histogram can take on, but there's a few common ones that I'll remind you that we talked about way back toward the beginning of the quarter when we started working about histograms. So it could be when I graph some data and I break it up into groups that all of the columns are relatively the same size. So if they're relatively flat, histogram, relatively flat. Anybody remember what we would call this shape?
Uniform?
Yeah, this would be called a uniform distribution. Thank you. And you know, some things are relatively uniform, some things are not. If I went to a second grade classroom of kids and I looked at their ages, they would be pretty darn uniform. They would be about the same age. If I went to an elementary school and I counted how many kids were in each class, and these were the grades down here, there's going to be about the same number of kids in each class. That'd be a uniform distribution. Rolling a dice, I get the same, roughly the same number of 1s and 2s and 3s and 4s and 5s and 6s. So uniform is just everything's about the same, uniform, same. Other times, there's other kinds of distributions that we've talked about. So we have symmetric distributions, and there's a bunch of different versions of symmetric. Something could be bell-shaped and symmetric. Let's use histogram boxes. And there's some distributions that are more triangular shaped, meaning that there's kind of a straight line going up through them and down to the other side. So we could say, hey, this is a triangular distribution, right? So I'm just kind of describing what the shape is. We didn't talk about this one, but I'm just, you know, messing around. Triangular. Just trying to remind you about what the word distribution means. And all it is we're looking at a graph and we're saying, well, what's the shape like? How are things bunched up? And sometimes we can use one word to describe it, but often it's like more than one. So for example, I might find a distribution that looks like this. So this does have a symmetric shape to it. So I could say, yeah, hey, this is symmetric. But I have these two stacks which appear to be about the same size. And if they were exactly the same size there, then this would be bimodal also. And something could be bimodal but not symmetric. Something could be relatively symmetric but not bimodal. It's all different kinds of shapes that we can have to a distribution. So again, distribution just refers to the shape of the graph. How does the data appear to be spread out? Where is it bunched up? So like here, the data is bunched up at very low numbers. It's also bunched at very high numbers. And there's very few data values in the middle. Here, we have most of the data values in the middle. It's bunched up in the middle, and there's very few on the left and very few on the right. And here, it's just like there's about the same everywhere, right? So if I pick a number like this one right here, the count of that number is the same as the count roughly of that number right there, whatever that number is in the data set, or whatever group of numbers. Normal distribution. So a normal distribution is a very special one, and it has a variety of characteristics. So I'm going to talk about the normal distribution in two different ways. First, from just like a histogram point of view, and then from a theoretical point of view. And I'll give you other examples of theoretical versus experimental. So it could be I graph some data like heights of adults. And what I'm going to find is that, you know, on average, maybe adult males are around 69 inches tall. So I'm going to find like most males are around that range. And then as I head out, these stacks decrease, maybe something like that. And it's going to be roughly the same as the other side on the other side. And this is not zero, by the way, that's a broken axis there. So let me send you about, what, 2 more here. And I think, if I remember right, the spread, the standard deviation of adult males is maybe around 4 or 5 inches, if I remember right, but I haven't looked that up in a while. I would find it's going to be a relatively symmetric distribution. So normal distribution as a histogram should be symmetric, is symmetric. It should also have a bell shape. So symmetric itself doesn't mean bell shape, it just means you could draw a line in the middle and the left side matches the right. Okay, so this is a symmetric triangular distribution. This is a symmetric bimodal distribution. This is a uniform, but uniform's pretty symmetric too, right? It's the same, if I draw a line in the middle, it's the same on the left as it is on the right. So there's tons of symmetric distributions. It turns out there's also tons of bell-shaped symmetric distributions, and normal is just one of them. And there's others, like there's a binomial and a ton of others I don't remember the names of, and some that don't have names. Normal distribution, 1 is symmetric, 2 is bell-shaped. And then way back in chapter 2, at the end, was an idea called the empirical rule. And the empirical rule related to if this was 1 standard deviation to the left, so minus 1s, and say this was 1 standard deviation to the right, so plus s, so 69 plus whatever the standard deviation is. So let's say the standard deviation was 3. So let's say sigma is 3, mu is 69, then this number right here, 69, would be what, 72, and this number would be 66 right there. If we went 2 standard deviations from the mean, so maybe that's about over here-ish, that would be plus 2 s's, which would be another 3, so that would be 75. And then what, roughly over here, let's say, would be minus 2 standard deviations from the mean, 63-ish. And let's go 1 more. So over here, roughly, would be plus 3 standard deviations. And then roughly over here would be minus 3 standard deviation. And let's say, what would that be? And plus 3 would be 78. And over here would be 60. And the empirical rule said we should expect to find a certain percentage of data within 1 standard deviation of the mean. Okay, so percent, oops, of data within, does anybody remember that percentage? 1 STD of mean. What percent?
Was it about 68%? Or
you nailed it, Michael. Yeah, it's about 68%. So if it's a normal, if the data is normally distributed in the population and we get a good representative random sample, we would expect about 68% to live within 1 standard deviation of the middle. So if we went into our list of numbers and we counted how many numbers are between 66 and 72, we would find that would be about 66% of the data would be in that range. If we then move on to say, okay, what percent is percent of data is within 2 standard deviations of the mean. Does anybody remember that one?
%85, I don't know.
Not 85, no, it led to our rare event rule. And the rare event rule says something's rare if it's in like the 5% fringe on either side. And so it's kind of related to that. So if we look within 2 standard deviations of the mean, then we're going to get about 95% of the data within 2 standard deviations. And then if we look within 3 standard deviations, so if we look at our data set and we count up how many numbers are from 60 all the way up to 78, then in that case, we get various numbers there. I think it's about 99.7, if I remember right, percent of the data. So 99.7% of data is within 3 standard deviations of the mean. And this altogether, this lower part, is what we refer to as the empirical rule. And the empirical rule, there's 2 ways to think about it. One, if your data is supposed to be normally distributed, then if you start counting within these boundaries, you should find those percentages of data items. On the other hand, if you don't know and you make a bunch of histograms and they're all pretty similar to this, then you're like, hey, the population's probably normally distributed. So if, when you sample data, you find histograms that are symmetric bell-shaped curves, and within 1, 2, and 3 standard deviations, you get these percents of the data values, then that means the population's probably normally distributed. Okay, so that's like the experimental version of what a normal distribution is. The theoretical version is a wee bit more weird, and I'll talk about theoretical versus experimental in a sec, but I need the textbook here. Oh, I opened it right there. All right. So back to 6.1, and let's pull this up. Human eyes, way back in the beginning. So when we graph a curve, like think back to maybe you took a college algebra class, you did some graphing. Here we go. For a curve to have this special bell shape, and there's lots of bell shapes out there, this would have to be the equation right there. So I'm going to copy that into my screen. So I want all of this here. Notice it says there, do not memorize that formula. It's not worth your time. We never need to use it directly. All right. So this is the formula for what we call a theoretical normal distribution, which is this smooth curve there. So, oops. So if I typed something like this into a graphing calculator, it would graph that for me. And it's not that much fun doing that, so I'm not going to do that. So this is a theoretical normal distribution. Oh, hello, Brett. I didn't see you join there. Welcome. Theoretical normal distribution. So there's the theory, and then there's the reality. So we'll take a minute to talk about that. The theory is that ideally, this is what, if you had tons of data, you know, like let's see, the US population is like 300 million-ish, and we wanted to sample all adult heights, and we went out and grabbed 1 million people out of that 300 million. So that's probably like half the adults in America. And we plotted the heights of every single person. It would be a relatively smooth histogram like this if we had lots of little thin categories, like maybe we went for, you know, 100 categories of heights. We would get something that looks like this. And based on the mean and the standard deviation, if we knew, we could calculate those from the data. If we were to make a histogram and then graph this with the calculated mean and standard deviation, we would see the smooth curve sits right on top of the histogram. But rarely do we have that much information. We just have these beliefs about it. So example of theoretical versus experimental, just to get that back in our heads, from probability, theoretical. So we're kind of taking everything we've learned in the course and throwing it together, but just focusing on things that are, quote, normal. Let's see, theoretical versus experimental. So experimental is where I do some sampling, and I'm just going to go pretty abstract here with dice, right? Dice has a sample space that is a 1 or a 2 or a 3 or a 4 or a 5 or a 6. And if I asked you what's the probability that someone rolls a 2, you would say, oh, it's 1 out of 6, right? Which is about 16%. Around 3 decimal places, it would be 0.167. 16.7%-ish. Right, so I just rounded there. And if I said, what's the probability of getting a 3, you would say, yeah, it's 1/6, right? So we have this theory about what should happen. So if I were to roll the dice 6 times, do I expect to get a 1, a 2, a 3, a 4, and a 5, and a 6 in some order? The answer is no. I might see a few 1s. That's possible. So if I make a theoretical graph of the probabilities, so here I have probability, and here I have the roll. I could either get a 1, or a 2, or a 3, or a 4, or a 5, or a 6. And let's say this right here is the value 1/6 on the number line. Then what I'm going to get is a uniform distribution. Every single number has the same probability of occurring. One, 2, 3, 4, 5, 6. It's theoretically, it's completely flat. However, if I experiment and I roll like 1,000 times, and I make a histogram, let's see, what's 1/6 of 1,000? That would be what, like 167-ish? So if I make this graph here, 1, 2, 3, 4, 5, 6, and this is the actual count, and say this is about 100 there, 100 rolls, and this over here would then be 200 rolls, then I would expect to get about the same number of 1s as 2s, but sometimes I might, just 3 had a bad day, and we get a little more 4s than 1s. So it's going to be relatively flat, but not exactly flat. Now with 1,000 rolls, it would probably be a bit flatter than that. But these would all be hovering around, so the midline here would be about here at 167 each, because 167 times 6 is around 1,000. Okay, so we have what happens in reality when we do some sampling, and then we have the theory behind it. So a normal distribution is this theoretical crazy graph here. Here's the equation of that graph. If I made it super simple, and I say, all right, let's let the mean mu be equal to 0, and let's let the standard deviation be 1. This simplifies dramatically, so that would be y equals 1/2 pi out front in a square root. That is a 0, so I have x minus 0, and that's a 1. X over 1 is x, so then I would get e, which is, I don't know if you guys remember e, it's like 2.7-ish. It's kind of a special number like pi, and then the oh shit, my battery's low. Hopefully I have the power cord from my drawing board. One sec. Uh-oh. It's usually in my bag of tricks here. Oh, thank goodness. So I do not want to draw with the mouse today. Does not sound like fun. Okay, we have power. Yep. All right, so then the equation would simplify quite a bit, but it's still a nasty equation. Like if this came up in a Math 95 or 111 course, most of the class would be like, eek, what the hell is this thing? Okay, so this is what the equation would simplify to, and he's like, that's not simple. Well, it's simpler than that, right? Then what I'm saying is right in the middle here, so let me draw a line straight down the middle. This right here is what I'm saying mu is. And remember, we've drawn pictures like this before. We've been drawing them for a couple of weeks now. So I'm saying mu is 0 right in the middle, and then standard deviation. So this would be about 1 to the right, 2 to the right, and 3 to the right. And then over here is 1, 2, 3. So this would be +1, +2, +3, because the standard deviation is 1. This would be -1, -2, -3. So if we ever make a graph of a normal distribution where the mean is 0 and the standard deviation is 1, those two facts together mean we have what's called the standard normal distribution. And if you remember way back to chapter 2, we talked about the idea of a z-score, and I'll remind you about what that is in a second. This is also the distribution of z-scores, or graph of z-scores. Distribution of z-scores. And what does a z-score do? You may or may not remember that back from chapter 2. All a z-score does is count standard deviations. So just a note from our way back memory of weeks past. A z-score is just a count of standard deviations from the mean. So over here, if my z is 2, that means I'm 2 standard deviations above the mean. Over here, if my z-score was 3, that means I'm 1, 2, 3 standard deviations below the mean. And to calculate a z-score based on data, there's a few different ways to do it, but the way we did it way back in chapter 2 was you take whatever number you have from the data set and you subtract from that the average of the data, or maybe the population, and you divide by standard deviation. So x minus mu, that's what we call deviation. And then we say, okay, so that's like how far is somebody from the mean, and now how many standard deviations in that, right? So if we divide, that counts up how many of these live in that distance there. So that's a whole bunch of stuff we covered before with some new ideas to kind of pull together where we're headed. Where are we headed? We'll get to that at the end of the week or next week. Why the heck are we doing this? Another example of theoretical versus experimental that we did before would be, remember we played with linear regression a few weeks ago? Linear regression lines. And there were a couple of examples I thought were wicked cool that you guys did some research on. And one of them was the honeybees, and the other one was the crickets. And if you watch a bee fly from its hive to some place, some flowers, it can get nectar, and then it goes back to the hive and tells the other bees about it by doing this cute little waggle dance. And if you compare the distance the bee traveled to the time, the length of the dance, your points line up, not perfectly, but pretty damn good. So that the length of the dance directly correlates to the distance the bee traveled. Is it perfect? You know, how do you tell when the bee started this dance and when is it done? Okay, so that's harder for humans to figure out. Bees probably get it down. And then since these line up, I can say, hey, this is the best line through those. So the red line here is the theoretical model. And then the blue dots, right, that's my experimental data. So the theoretical is like the ideal, the experiment is reality, and reality is always a bit messy. And we have these math ideas that kind of match reality. But our math is what we call kind of ideal and perfect, and reality is not. Like, can you find a real perfect circle in reality? And the answer is no, I don't think so. There's things that are very close to circles, but nothing's perfect. Okay, so normal distribution. So let's use a normal distribution in context. Let's see. Trying to remember, I had an idea. Oh, I know what I want to talk about. Back to my drawing board, new page. So not every data set is normally distributed. Some are not. Things that tend to be normally distributed often are measurements, but not all measurements are, like measurements of say, humans and other animals. Heights of humans are relatively normally distributed. Heights of humans have a normal distribution. Standardized test scores are often normal, but not always. Standardized test scores are normal. And I don't know if you've ever questioned what the hell does standardized mean? Often when you take a test like an SAT test or the graduate record exam or some other test to get into some program or area, there's a raw score and there's a standardized score. And so basically what standardized means is they kind of force it to be normal even if it's not. So often standardized, this word here, when you see it with test scores, often means forced to be normal. So if you were to get all of the test scores and you graph the raw scores, that might be a wacky looking distribution. It might be relatively bell-shaped, but not perfect. Whereas if you graph the standardized version of the test score you received, that graph would be like almost perfectly normal. So it's a little math jiggery-pokery people apply. So if you've heard about instructors, what do they call it, curving the grade, that means they're trying to force it to be normal. And the danger to that is it assumes that grades should be normal. Like very few people should get A's and very few people should get F's, but most people should get C's. However, from the point of view of a student, every student wants an A, right? So should grades be normally distributed? And that's a strange, difficult question to answer. So anyway, so I'm going to go do a standardized test example, and I'm going to use SAT. SATs, oh gosh, I forgot the numbers now. I think the mean is either around 800 or 1,000. Anybody remember what average SAT score is? SAT score. 1,200 is good. What is average? I think it's usually around 800. About 1,000, okay. All right, let's just go with 1,000. Oops, come back graph. There we go. So SAT, let's say the population mean is 1,000 for the standardized score, and the standard deviation, let's say that's 200. And these are normally distributed. So a student comes to me, and let's call them student X, and they say, hey, I got an 800 on the SAT. How did I do? So I'm going to grab, I'll just draw my own, what the hell. My best bell-shaped curve. So kind of like we've been drawing these for a while now. Draw your best. Oh, let's try that again. Good enough. Okay, so there's my best symmetric normal curve, and then there's my mark for the middle. That's the median and the mean if it's symmetric, and I'm claiming that the mean is 1,000. And then maybe around right here is 1 standard deviation above, 2 standard deviations, 3 standard deviations, and then going the other way, this would be about 1 below, 2 below, and 3 below. And if the standard deviation is 200, then that means this should be a 1200, and this should be a 1400, and this should be a 1600. And going the other way, this should be an 800, and a 600, and a 400. And so I have a student that claims that they got an 800. Now, with a theoretical normal distribution, we can't find like the probability of getting a particular score, but we can find the probability of getting a range of scores. And then the reason is there's supposedly infinitely many scores somebody can get. So one number out of infinitely many is a 0. So with a theoretical distribution, the probability of getting any one number is 0. So we have to look at ranges. So what I could tell the student is what % of students had scores lower than them. So this region of the curve here would be, usually with these curves, we talk about percentages, not actual numbers. Percent of people who scored lower than 800 on the SAT. So I can calculate that using a normal distribution calculator. So to do that, I need something like a TI calculator, which I don't use, or I need a spreadsheet, or I can use StatKey. So I'm going to jump to StatKey to get that number for me. I can kind of estimate it using the empirical rule. So I'm just going to make a quick estimate on this. So the way I would estimate this is thinking about the empirical rule. If this is the mean, mu, and this is one standard deviation below and one standard deviation above, the empirical rule said that 68% of values should be within that range. Okay, if there's 68 in the middle, 100 minus 68 is what? 32? That gives me 10, carry the 1, yeah, 32. So that means the tails have 32 to share. So that means this left tail here should have about 16% of the data, and this right tail here should also have about 16% of the data. So what I could tell this person is that about 16% of people scored lower than you. Now that would put them in the 16th percentile. So this is about a score of 800. 16th, if my guess, my estimate is right. Percentile. So P16, remember percentiles from way back, is approximately a score of 800, according to this. So let's look it up in the StatKey generator. Browser, StatKey. And we are doing, in this case, a theoretical normal in StatKey. And to use it, you have to go set the mean and the standard deviation. So 0 and 1 means this is the standard normal, or we're talking about z-scores. I'm going to use 1,000 is what my claim for the mean of SAT scores was, and my claim was that the standard deviation is about 200. All right, so I set the mean and it resets that. Now these numbers over here don't always work out nice. They happen to work out to be the standard deviation, but that's not always the case with these graphs on StatKey, unfortunately. I'm going to do a left tail, and I want to set that to 800. Because they got a score of x equals 800, and I hit OK, and StatKey says it's about 0.159. Okay, so it's almost 16%. So they're just a touch less than the 16th percentile. So at first it's like, hey, I didn't do too bad, right? I only got one standard deviation below, but that means you're in the 16th percentile. So if you're in the 16th percentile, that means 16% of the people did worse than you. However, what percent did better? That would be 84% did better than you. Damn, I would like to score higher than that. I would at least like to be a little above the, the 50th percentile, which is 1,000. Okay, so then let's say another student comes to me. So let's say this can be student X2, and they said, hey, I got a 1,200 on the SAT. I'm like, man, that's great. Let's figure out what, how good that is. Well, it's certainly one standard deviation above. And if we calculate the z-score for that, we take our x value, 1200, subtract the mean, 1000, and divide by the standard deviation. So 1200 minus 1000 is 200, over 200 is exactly 1, right? And it's a positive 1, which means they are 1 standard deviation above. Remember, a z-score just says, hey, how many standard deviations were you above? And it could be a fractional number, right? It could be somewhere in between here. What percentile are they? So they are what percentile with a score of 1200. So if I make a mark here at 1200, what percent of people scored lower than this person? Well, since 1 standard deviation below put about 16% below, then 1 standard deviation above should put about 16% above. So I'm going to guess that's the 84th percentile, kind of based on this drawing right here. But we can go check it by using a calculator. So I just want to change that number to 1200. And I'm doing a left tail because I'm looking for, what percent was below that score. And this says, yeah, about 84%. So they're in the 84th percentile. Let's go, where'd it go? There it is. So this would be P84, 84th percentile. So I would tell the person that got the 1200, hey, that's pretty good. You should check to see what kind of scholarships that would give you. The person that got the 800, I would say, it's not horrible, but it's not great. 84% of people did better than you. I think you should study some more and try taking the SAT again. Because I bet most colleges are hoping you're above 50%. Now, colleges take a wide range of SATs. They don't just look at SATs. And some schools, like community colleges, don't look at SAT scores at all. All right, I'm going to pause this recording.